Thank you very much. There are people among you with microphones, so I'm sure many of you have questions. If you could raise your hands, and we'll send someone along. Gentleman on the second row over there, if you'd like to stand up, tell us your name, give us your question in a good loud voice.
Hello, I'm Robert Chambers, a retired physics teacher, and my question for Professor Shears is this. Prince Louis de Broglie, the scientist, predicted that there's an associated wavelength for every particle, but why should the converse be true, that there's an associated particle for every wavelength?
Well, what you're referring to is wave-particle duality, and this is a really interesting aspect of modern physics and quantum theory, in the sense that classically, physicists regarded forces being propagated by waves. Light was a wave. After quantum theory, and particularly in particle physics, we take the point of view that, well, we can also adequately, or just as well, describe these things as particles. And I'm afraid particle physicists are the worst of all for this, because we always imagine everything's a particle, regardless of what it is. If there's an effect there, it must be communicated by a particle and not a wave. To some extent, they are two different sides of the same coin, because when it comes down to it, there is no such thing as a wave. There is actually no such thing as a particle. The real, true explanation lies somewhere in between, in some quantity that can display the properties of both, which is a really subtle thing.
Thank you very much. Anyone else? Young man up there in the green.
You mentioned that the alpha experiment was creating antimatter and analysing it. I'd just like to know how it was creating the antimatter.
Oh, that's quite a tricky one. So, good question. It's taken them years to be able to do it. So the very first thing you have to do, well, you need two things. You need antiprotons and you need anti-electrons. So your first challenge is to get samples of both of those. So at CERN, there's actually an accelerator called the antiproton decelerator. It's a really nice name. What it does is it makes samples of antiprotons, ultimately from hydrogen, from a gas bottle, firing or ionizing hydrogen to get protons, zipping it through targets, and in this process, you get antiprotons being produced. And you can separate this off using a magnetic field because antiprotons have a different charge to normal protons. That gives you a sample of antiprotons. Anti-electrons, positrons, you can get sort of through equivalent processes. Then you have to bring these together and somehow get them to link up to form an anti-atom. And that's really, really tricky because normally these things don't necessarily want to go near each other. The trick is to really cool them down, to give them so little energy that when they get close, they don't have enough energy to move away, and they just sort of fall into a mutually convenient orbit around each other and then settle into the fact that they're now an atom, rather a bound state, rather than two things zipping around separately. And it's not a trivial thing to do. It did take Alpha the best part of 5-10 years to be able to cool things down sufficiently to get anti-hydrogen atoms being produced, and then to detect the fact that they had them. And unfortunately, the only way to detect the fact you have an anti-hydrogen atom is to see its aftermath when it's annihilated, so they could only find it to start with after the fact. But that's the basics as to how you make an anti-hydrogen atom. Does that make sense to you? Okay.
The television presenter on the second row.
I've got one of those T-shirts with the standard model on, which I got at CERN. I was wondering, in your opinion, am I going to need a little patch to sew on it to make sense of it? Or am I going to need to get a whole new T-shirt, and how big is that T-shirt going to be?
You know, I think there's a great marketing opportunity here. I think we should just develop an entire wardrobe of possibilities here.
Gentleman on the end there.
Yes, hello. Yes, I was wondering, you mentioned that they're close to coming up with a possible new phase of matter, and that might have existed in the early universe. So any progress towards finding out exactly what that would be like?
No. Well, it's hard. It's really hard. This was an entirely unexpected observation. To some extent, hints of it have been seen in other experiments, other heavy ion experiments at lower energies. But this was a really distinctive feature that you couldn't ignore when Atlas and CMS analysed this heavy ion data. And to sort of put it in context and tie it into a theory and then understand what it's telling us about what matter is doing, no, we don't have that yet. We just have the observations, and theorists are trying to link that in with models of the way matter links together and coherently forms a nucleon from being some sort of plasma. But there is no good explanation yet. And the other thing to remember is that even if you develop a theory that will explain this, you still have to test it. And that's why we're going to have another heavy ion run this autumn. So hopefully we'll be able to explain this a little better. Now, I'm being a little disrespectful here. In fact, there are predictions, or there are models that try and explain this. And the reason I'm being a little hand-wavy is that I don't really understand them. They are an unexpected spin-off of string theory that can give extra information as to what goes on inside these messy heavy ion collisions. And so you can actually use string theory to predict what should happen, and that seems to fit this particular effect that was seen. But we can also make other predictions which we would then like to test, and that's what we hope to do with a heavy ion run later this year. And until we can do that, we can't be sure whether we've got a better explanation or whether we've just invented something that fitted the data that wasn't correct at all. So that's what I mean when I say there hasn't really been progress yet. There's nothing we've been able to test and then be confident of.
Up in the gallery?
Okay.
Yep. I just wondered, given that what we know the speed of light to be, and that we're only talking about 7 kph, and a relatively short distance, if it was only as far as Italy, is that really outside the bounds of experimental error, that measurement? I mean, is it really statistically significant at all?
Well, according to the opera collaboration who presented these results, yes, it is. This measurement, although it seems small, the difference with respect to the speed of light seems small, that difference is measured extremely accurately. So this difference is 6 standard deviations, which is a probability of, I don't know, it's 99.9999999%. It's very unlikely, provided you've estimated all your uncertainties correctly, that is a random fluctuation that just happens to fortuitously give you that. It satisfies all our criteria for discoveries and everything else. It is an incredibly precise measurement. It's a short enough distance, 730 kilometers, but that distance is measured accurately using GPS technology and good surveying as well. And the time taken for the neutrinos to travel is measured using atomic clocks and the requisite technology there. And if you look at the systematic errors that the opera physicists have put on those measurements, then they are small, but they're not unreasonable for those technologies. They are 2 measurements that you can make extremely accurately. Speed is just distance covered in the time you measure. So if you've measured distance well and you've measured time well, that means that you measure speed well as well. And that's what opera claimed to have done. And this is what has generated all the debate as to how precisely you can actually measure those quantities. Is that distance actually known to the precision that opera say it is, to some 20 centimeters over 700 kilometers? Is that time known to the precision that opera think it is? And that's the key to understanding this measurement. Because, of course, if it isn't, then that measurement isn't significant, and then the neutrino speed becomes consistent with the speed of light or just under the speed of light, and Einstein is saved again.
So we may yet get to see a well-known physicist eating his shorts on live TV.
I believe we have another question up in the gallery. Run.
Dr. Shears, now at CERN you've got your Large Hadron Collider. What is the next large experiment that the new generation of particle physicists are dreaming of doing at night? And what sort of machine would it be, and what would it be searching for?
Ah, good question. It's a really good question, actually, because it's so difficult to answer. There's, in the sense that there's no point dreaming up a new facility if you don't have a good idea what to look for. And the LHC was a sort of obvious step after our last generation of accelerators because it took us that step beyond and covered the region where we expected the Higgs to be. If it existed, we would find it with the LHC, and also a good region of where we might expect to see supersymmetry, so we could work out about dark matter. So there were very good reasons for designing the LHC in the way that we did. But as to the next step, it's not at all obvious. It really depends on what we see inside the LHC. So, for example, if we make a discovery of the Higgs, and the Higgs, let's say, has a mass of about 120, then we really need to understand what's going on with that Higgs. We need to understand how it behaves. We need to know how it's influencing other particles. And then we might design the next facility to hone in on that. We might tune it to just become a Higgs factory, if you like, and just make lots and lots and lots of these once we know the energy we have to run it at, and then fulfill the role of really understanding what's going on in that sector. If we don't see it, then something has to fulfill the role of the Higgs in our theory, and if it's not the Higgs, it's something completely other. And then what you'd ideally like to do is devise a facility which goes to the maximum energy you can imagine, because that's our best way of throwing our arms open to the universe and going back to earlier times and really trying to look to see what's out there. But technologically, that's not possible either, because we're operating pretty much at the limit of superconducting technology for the LHC. So it's a very tricky question. And, of course, people are trying to design the next facility. In fact, the LHC itself will be upgraded to run at greater beam intensities and to even up the energies, which is possible there. And people are also looking at different types of accelerators that could then be used to focus on a particular energy if we do make a discovery, like the Higgs and supersymmetry, so that we won't be left behind when that happens. We'll know how to do it. But without knowing what's out there, it's very difficult to just put all your eggs in one basket, if you like. We're keeping our minds as open as possible because we really don't know what's in the universe yet to look at. I mean, if there's nothing there, then we really have to think of different ways of investigating this and perhaps go to neutrino experiments, experiments in outer space using high-energy cosmic rays, particles for outer space. Have to think differently. So there's no set answer yet, I'm afraid.
Gentleman out front.
Thank you. Of course, one of the theories that's very popular is that gravity is apparently so weak because, in some sense, it's escaping to many more dimensions than 4. If there were many more dimensions than 4, how would that affect your search for things like the Higgs boson or anything else? Or how would it affect the standard model?
Well, good question. There are some varieties of theories that invoke these extra dimensions of space that do have measurable, testable predictions at the LHC. And some of them, particularly the ones that involve large spacings between dimensions, involve new particles which we might be able to discover. Now, these new particles are really echoes, if you like, of the way that existing particles travel in the dimensions that we don't see. But some of them may be visible to us in the form of particular characteristic signatures being produced far more often than we would expect at the LHC. So that's one way we can test them directly. Now, we have looked for those already, and we haven't seen any evidence yet. So if they're there, they're hidden in such a way that they're not really influencing anything that we've measured so far, because our standard model measurements are right on the nail. You saw that our measurements of the strong force, W boson, Z bosons, they're all exactly as we expect. So if there are extra dimensions there, they haven't influenced anything yet. I did hear, actually, an argument that said that extra dimensions could explain this speedy neutrino business because it would provide a shortcut for the neutrinos to sort of somehow zip through, and they would actually cover less distance than you thought in the time available. Well, think what you want. No, it's very difficult to test, and there are lots of theories that also claim to predict ways in which extra dimensions could influence the type of Higgs particle that you might see. But again, without having discovered a Higgs particle to be able to compare to, it's hard to know how good those theories are. So yes, there are predictions for this sort of thing, and we will be able to test them once we find something, or even if we don't find anything, that will rule them out. But as yet, we haven't seen any evidence for these things or anything that needs to have these things invoked to explain them.
Thank you.
Yes, gentleman in the orange.
Yes, I just wasn't very clear when it came to searching for the Higgs. You've got the graph with the U on it, with the mass against electron volts, I think it was. Is the CERN experiment capable of looking at the whole U? What did it go up to, even at the second phase?
Oh, this is really, really interesting. So the plot I showed you here applies to the version of the Higgs which we have in our standard model. Now, this is where all the caveats that particle physics have come in, because this is the simplest version of the theory that you can have. It needn't actually be the version of the Higgs that's there if the Higgs is there. If the Higgs is there and it's simple, which is always a good guiding principle, then what this plot means for us is that we have to find it where the y-axis is less than 4, okay? Which means once you combine it with the experimental limits, then you're very constrained. It has to be between 150 and 114. Now, that's just if the Higgs is like that. If the Higgs is more complicated, then this analysis does not apply at all. And you can't use this, it doesn't count. But there is a hard limit as to the maximum mass a Higgs can have. And that's because I said that it formed part of our standard model because it made our predictions make sense. And if the Higgs goes above a certain mass, then the ability of the theory to keep the predictions making sense falls at a certain stage. And that falls when the Higgs has a mass of about 700 GeV, 800 GeV. So right out, I don't know if it's on this plot. No, not on this one. These ones stop at 600. But right out there. Now, the reason that that's interesting is because there's a process that can occur at the LHC involving pairs of W's scattering off each other. And if there's no Higgs, the prediction for this is it's infinite, it's stupid. You know, you're getting energy for nothing. So if we don't see a Higgs by that stage, by those energies, then we can make a measurement of this process, which we can do, which is reasonable. It's going to be completely at odds with predictions. We cannot make the standard model fit what we observe in data at all. There has to be something there. And the LHC has been designed to sweep through the region from 0 up to 1,000 GeV and beyond. So it really was designed to take that into account as well. So that's what I mean when I say if the LHC doesn't find the Higgs anywhere, then we really do have to throw out that theory because there's no way for it to survive at that point. Although I have to say there are theories coming up now with theories called hidden Higgs, which... so, you can never keep a good theorist down.
That sounds like cheating. We're running a bit long time, so I'm going to ask the last 2 questions. Anyone around here? Oh, sir, on the... I'll come to you. I'll come to you next.
Hello, yes, there are inherent uncertainties in colliding composite particles, as you are at the LHC, in the actual energy collisions, the energy of the collisions. Can you sort of quantify those uncertainties for us and what it means for what you won't be able to tell us, even if you get a positive Higgs signal?
Now, that's a really important point because, as you said, a proton it's not fundamental, it's made of quarks. And if you look hard enough and deep enough between the quarks, you have all sorts of quantum mechanical mess going on involving the strong force of operating. And when you have 2 protons colliding, then you only have some part of one proton actually interacting with some part of the other one. So you're quite right. All of our predictions rely on the fact we understand what's going on inside the proton and what it's doing. Now, that knowledge does limit our predictions, I'll be quite honest. But we do know that behavior to within, at the moment, about 2 or 3% for most of the processes that we're looking at. And you can see that the experimental proof comes with this plot of the strong force, because we're measuring the rate at which quarks are being produced and comparing to theory. That theory is not just our prediction for how much quarks are produced, it's how often they're produced, bearing in mind your colliding protons. So it includes the uncertainties that we have in knowing what goes on inside the proton. So you see it's behaving very, very well. And in fact, we can only just improve our knowledge of what goes on in the protons by adding the information that LHC data gives us at this higher energies. So it's not perfect, our knowledge, but it's not bad. 2 or 3% is about the limit of our theoretical predictions in any case, and we expect it to get better. So that's not going to limit us when it comes to searching for the Higgs or making discoveries, although it is a good thing to point out.
There's someone with a question up in that.
Hello. The collisions, up here, hello.
Okay.
The collisions are very energetic, so is the debris. The passage of the debris through the sensors, which registers and gives you your data, how badly does it degrade the sensors? How often do you have to replace components?
Well, we haven't had to replace any yet. So the radiation is the problem. So charged particles passing through it's just like a big radiation dose. So it's the particles closest to the beam that see the greatest density of particle production. So it's these silicon detectors that I showed you a picture of sort of about halfway through the talk that have the shortest lifetime, the shortest working lifetime. Now, we've designed these detectors so that they should be able to take data for 5 years at nominal performance before they need to be replaced. And that was a prerequisite in the design because we knew what an example LHC schedule would be. We knew that there would be a long shutdown to enable us to make a replacement at that stage. So we had to put that into the design and make them radiation hard enough to survive that length of time. So at the moment, we're still operating with our first round of detectors. At least for LHCb, we're building a replacement silicon detector that will go in the long shutdown because we think by that point we'll have received such a large effective radiation dose that our response will be degrading. We won't be able to recoup it by doing any of our normal tricks like raising the voltage to collect more charge or anything like that. And if the LHC then upgrades to have much more powerful beams or upgrades its energy, then the detectors have to upgrade again. They have to upgrade all the electronics because they'll need to take decisions faster and read out detectors faster. They'll have more particles being produced, so they have to deal with that greater radiation sort of hardness issue. And every experiment has a program of upgrade research going on. They're not building detectors for the upgrades yet. They're really investigating the technologies to see what would give them the best answer to this. So you're right, our detectors don't live forever. We do replace them, but we use that opportunity to delve into the latest technology to see if we can get more from the way in which technology has moved on in the time since we built the last one. So we're designing complete replacements for about 2020, that sort of time scale.
Okay. All right, so thank you all for coming, and I'm sure you'll join me in thanking Dr. Shears for
zipping it through targets, and in this process, you get antiprotons being produced. And you can separate this off using a magnetic field because antiprotons have a different charge to normal protons. That gives you a sample of antiprotons. Anti-electrons, positrons, you can get sort of through equivalent processes. Then you have to bring these together and somehow get them to link up to form an anti-atom. And that's really, really tricky because normally these things don't necessarily want to go near each other. The trick is to really cool them down, to give them so little energy that when they get close, they don't have enough energy to move away, and they just sort of fall into a mutually convenient orbit around each other and then settle into the fact that they're now an atom, a bound state, rather than two things zipping around separately. And it's not a trivial thing to do. It did take Alpha the best part of 5-10 years to be able to cool things, particle duality. And this is a really interesting aspect of modern physics and quantum theory, in the sense that classically, physicists regarded forces being propagated by waves. Light was a wave. After quantum theory, and particularly in particle physics, we take the point of view that, well, we can also adequately, or just as well, describe these things as particles. And I'm afraid particle physicists are the worst of all for this, because we always imagine everything's a particle, regardless of what it is. If there's an effect there, it must be communicated by a particle and not a wave. To some extent, they are two different sides of the same coin. Because when it comes down to it, there is no such thing as a wave. There is actually no such thing as a particle. The real, true explanation lies somewhere in between, in some quantity that can display the properties of both, which is a really subtle thing. It's down sufficiently to get anti-hydrogen atoms being produced, and then to detect the fact that they had them. And unfortunately, the only way to detect the fact you have an anti-hydrogen atom is to see its aftermath when it's annihilated. So they could only find it to start with after the fact. But that's the basics as to how you make an anti-hydrogen atom. Does that make sense to you? Okay.
The television presenter on the second row.
I've got one of those T-shirts with the standard model on, which I got at CERN. I was wondering, in your opinion, am I going to need a little patch to sew on it to make sense of it? Or am I going to need to get a whole new T-shirt, and how big is that T-shirt going to be?
You know, I think there's a great marketing opportunity here. I think we should just develop an entire wardrobe of possibilities here.
Thank you very much. There are people among you with microphones, so I'm sure many of you have questions. If you could raise your hands, and we'll send someone along. Gentleman on the second row over there. If you'd like to stand up, tell us your name, give us your question in a good loud voice.
Hello, I'm Robert Chambers, a retired physics teacher, and my question for Professor Spears is this. Prince Louis de Broglie, the scientist, predicted that there's an associated wavelength for every particle. But why should the converse be true, that there's an associated particle for every wavelength?
Well, what you're referring to is wave...
Anyone else? Young man up there in the green.
You mentioned that the alpha experiment was creating antimatter and analysing it. I'd just like to know how it was creating the antimatter.
Oh, that's quite a tricky one. So, good question. It's taken them years to be able to do it. So the very first thing you have to do, well, you need two things. You need antiprotons and you need anti-electrons. So your first challenge is to get samples of both of those. So at CERN, there's actually an accelerator called the antiproton decelerator. It's a really nice name. What it does is it makes samples of antiprotons, ultimately from hydrogen, from a gas bottle, firing or ionizing hydrogen to get protons,